This video documents the removal of a defect found inside the shuttle main engine 2 liquid hydrogen feed line in the orbiter Endeavour. The defect is located on a slot on the mid-bellows bistro flowliner, which is approximately 5 feet inside the feed line and impossible to reach with a conventional tooling. The slot defect was located at approximately the 1 o'clock position. The defect was a partial punch of the flowliner slot created during the manufacturing process of the line.
The tool used to remove this defect was designed and built by the NASA prototype shop at Kennedy Space Center. The tool was mounted on a pole so it could be extended into the line through the engine interface flange. The cutting head, which is the portion sticking up, actually inserts through the flowliner slot. Then the tool is clamped into position onto the free edge of the flowliner using the brown Vespel clamp. The clamp helped to ensure that the cutting head was properly aligned on the slot during cutting.
Due to the location of the defect, we had to set up 2 borescopes to be our eyes, one looking at the slot from the inner diameter of the line, and the other was fed through an adjacent slot to get a view of the slot from the outer diameter. The tool is being inserted into the line in position. The mounting fixture on the pole attached to the 2 bolt holes at the engine interface provided stability for the cutting head by securing the other end to the tool.
While the operation was going on, the rest of the team was able to watch the video feed from the borescopes real time. The tool operators for the job were also the tool designers, so they were very familiar with the tooling and had done many practice runs on a test feed line inside their shop. So by the time they were ready to cut on the vehicle, they'd done multiple practices and were very comfortable with the job.
The double punch created an area of displaced material on the slot, which was estimated to be displaced approximately 25 thousandths of an inch. For reference, the overall slot width is 250 thousandths of an inch, and the material thickness is 50 thousandths.
You can see the view from the outer diameter of the flowliner on the left side of the screen, while the view from the inner diameter is on the right. You will see the cutting head being positioned on the inner diameter camera, and once it's inserted into the slot, it will be visible on the outer diameter view. Keep in mind that the views you're seeing are magnified. For reference, the width of one of those slots is just 1/4 of an inch. You can see on the back side of the flowliner the displacement that was there from the original punch. You can also see that this area was actually ground down some before the flowliner was installed inside the line. X-rays from the original build of the line showed the defect was present then, so this defect had flown 19 times. Once the cutting head is inserted into the slot and secured, the head was drawn through the flowliner material, removing the defect and drawing into a cavity inside the tool head. Since the defect was located on the downstream side of the flowliner, the cutting edge is seen on the side facing the clamp.
When the defect was originally found, a series of double-punched test coupons were made to evaluate the acceptability of the defect and the potential for it to liberate during engine run. Due to the location of the flowliner in the feed line, if the defect came loose, it would be transported directly into the inlet of the low-pressure fuel turbopump on the engine. There are no screens or filters in between. Extensive evaluation of the test coupons showed micro cracks approximately 5 to 8 mils long in the transition area between the defect and the parent material, which meant we couldn't build rationale to say we could guarantee the defect would not come off at some point in the future. In other words, fly as is. Additionally, analysis by the shuttle main engine community said that the piece of that mass was greater than the critical impact mass for the low-pressure fuel turbopump turbo blades. Once those answers came in, it was decided that the defect had to be removed. The alternative to removing the defect in place was to remove the entire feed line. That's a huge job. That would have required the removal of multiple pieces of flight hardware, not only from the main propulsion system, but also the water spray boilers, an auxiliary power tank, the electrical wiring, as well as development of new ground support equipment to maneuver the line outside the ship around the vehicle aft thrust structure.
You can see as the cutting edge comes up through the outer side of the flowliner, drawing the defect into the tool head. This is to prevent it from coming loose inside the feed line. This was a critical feature of the tool because if that removed portion had gotten free, it would have been extremely difficult to find it inside the line and remove it. Once cutting was complete, the clamp was released and the tool was removed from the slot, and then removed from the feed line, when the cutting head still retracted to keep the piece securely retained inside the tool head. Once the tool was safely outside the feed line, the cutting head was extended and the sliver was removed from the tool so that we could get our first up-close look at it. Once we were able to get a good look at the removed sliver, we could see that it came off in one crescent-shaped piece with no jags or burrs. An additional part of the test coupons we had done showed that the slot edge that the tool left behind was as good or better than the original punched slot edge. This repair was a combined effort of the NASA prototype shop designers and machinists, as well as the MPS and M&P communities at multiple NASA centers. From the design of the tooling, evaluation of test coupons, and engineering support through the entire program board approval process, the cooperation, skill, and collaboration of the entire team really helped to make this operation a big success.